Hey guys, today we're going to take a look at concavity, I don't know how to say it, concavity, and points of inflection. So there's two possibilities here. We can have a function be concave up or concave down. So for a function to be concave up, what it is that the slope of the function, or the derivative, is going to need to be increasing. So it's increasing. Okay, and so it's concave up over that interval as long as the derivative is increasing. And similarly, if the derivative is decreasing, then it's going to be concave down, okay, or downward concavity. So is decreasing. Okay, so what this looks like, if we look at these graphs, okay, this is this is concave upwards. I keep doing that. So it's kind of cupped up. So this is what we call being concave up. Okay, and then similarly, if it's cupped down, it's concave down. All right. So if we look here, we've got this fancy graph over here, and we want to find the intervals that it's concave upwards and downwards. So we'll say upward, okay, and we'll just do our intervals here. So the ones that it's cupped up, we've got between A and B, or sorry, what am I doing? So between A and B, so the interval would be from -5 to -3. Okay. From B and C, it's concave downward, so we'll skip that for now, and we'll look in C and D. Concave, so that's between 0 and 3. Okay, and then it just resumes at 3. Okay, the point 3 isn't included, so that's why we have to split it up into separate intervals here. And then at E, which is 6. And so those are our intervals that are concave upward. So downward. Okay, we just have what's left over. So the first one leading up to the A, so it starts at -8 and goes to the -5. Okay, and then we've got between -3 and 0, and then we've got from 6 to 8. All right, so those are our intervals that are concave upwards and downwards. So it's easy to see whether it's concave up or down when you're given the graph, of course, but we're not always given the graph, so we're going to do a test here. So what you're going to end up doing is you're going to do the second derivative. And what you'll find is that if the second derivative is greater than 0, then that's going to be concave upwards. Concave, zoom. Okay, so it's concave upward. And similarly, if it is less than 0, so if you get negative values for your second derivative, then that's going to be concave downward. All right, so the only other option, of course, is that it's actually equal to 0. Now, if it's equal to 0 over an interval, that means that the slope is not changing. So the slope is remaining constant over that interval, in which case it would, of course, be linear. Okay? So there it is. All right. So there you go. So let's jump over to the second page here. Oh, no, that's not. Oh, I can never get this thing to work. There we go. All right. 18th time's the charm. So we're going to find the intervals of concavity for this function here. So the first thing we're going to do of course, is we're going to find the second derivative. So before you can find the second derivative, you have to find the derivative. So f prime of x, so we'll get that that's 4x cubed minus 6x squared. So that's our first derivative. And then we do our second derivative, and we get 12x squared minus 12x. So now what I'm going to do is I'm going to factor this. So I'm going to factor out a 12x, and I'm left with x minus 1. All right. So if we so what we want to do is we're going to find the intervals between it being, between the zeros, basically. So we're going to have to set this equal to 0. Okay. We set that equal to 0, and then we get that x equals 0 or positive 1. Okay, if that's equal to 0, x is 0 or positive 1. So these are going to tell us where our intervals are, because at this point, this is at the point where it's the slope is not changing. Okay. So now what we can do is we get to do another one of these interval charts that we love so much. So, and we're going to write out the intervals as, so we'll have x is less than 0, and then we'll have x is between 0 and 1, and then we'll have x is greater than 1. So those are our possibilities there. All right. So what we want to look at then is for those values, what is the sign of the second derivative? So when we look at it, if x is less than 0, if we were to sub a number less than 0 into that second derivative, it would give us a positive number. And so you can test that. You could use -1 or something like that, and it will give you a negative number. If we pick a number that's between 0 and 1, it's going to give us a negative number. And then if we pick a number greater than 1, it's going to give us a positive again. So what this tells us is which way this is concave. So the concave, so if it's positive, that's going to be upwards. And if it's negative, it's going to be downward. Okay, and then this one will be up again. Right, so there we go. So we know that it starts concave upward, begins become concave downward, and then becomes concave upwards again. Okay? So it tells us to go back and look at example 1 and identify all the points of inflection. Now, where did that go? Am I jumping the gun? Oh, I'm jumping the gun. Sorry, we haven't looked at points of inflection yet. All right, so what is the point of inflection then? So a point of inflection is where we transition between being concave upward to downward or downward to upward. So this is where f of x changes from concave up to down, or vice versa. Okay. The other thing that has to happen here is at the actual value, the second derivative will either equal 0 or be undefined, so it does not exist. Okay, now, I shouldn't say it does not exist. It's actually undefined. We'll say undefined. That's just a better word to use. Undefined. There we go. Okay. So we've got some examples over here. Now, we don't traditionally think of this one up here in the corner. That's not really what we think of, but that is technically a point of inflection. These are the ones that, these other three are more what you think, and you can see that you would have, yeah, well, whatever. You can see what they look like. So it's the transition from concave up to down or down to up, okay? So if we go back to that example 1 and we say, well, what are the points of inflection? You would have A, B, C, and E. And D, don't be deceived by D. You can flip over and look at it if you want, but it's concave upwards, and then it's undefined, and then it becomes concave upwards again. So it's not actually a point of inflection for that one. All right. Yeah. So we're going to use the sign chart from example 2 to identify the points there. Well, this one's fairly simple because we had two possibilities, 0 and 1, and of course it did alternate both times. So it would be at x, so we'll just write that as the points as 0, f of 0, which actually is just 0. So I guess I can write that. So it's 0, 0, and then we had when x was 1, which would give us -1. Okay. So there you go. So, second derivative test. So let f be twice differentiable. So that's just telling us that it is possible to take the second derivative. The other sort of little trick here is if we take this second derivative at a given point, that's the 0. So if you find a turning point by using the first derivative, okay? So you take the first derivative, you set it to 0. You find the zeros using that way, and then at those same values you test the second derivative. What you'll find is that if you get a positive number, okay, if you get a positive number, then that point is a minimum. Okay, I'm going to zoom in so it's okay. And alternatively, if you get a negative number, it will give you a maximum. All right, so there we go. So these are just some examples here. So yeah, so this one's not a max or min, so we knew it was a point of inflection, and then you just do your concavity test. But this one here, you can see it's a minimum point. When you take the second derivative, you will get 0. What? Hold on. I read this wrong. Oh, whatever. Anyway, you understand. All right. So that's basically it. Example number 5 and 6 are what you are going to do, so we can try them out at the beginning of the next class. So until next time, go Sabres.